So when you have an extended object where the mass is not all located at one spot, you cannot use the simple pendulum formula. You have to use the relationship for a physical pendulum. And recall that that is a formula that is not given to us. T equals 2 pi times the square root of I sub p divided by mgh. And we'll talk through what all those things mean as we go through this example. So first of all, I sub p, so that refers to the inertia as this object rotates about point P. So the inertia formula for a thin rod, of course, is 1/12 ml squared, but that's assuming that the rod pivots at its center of mass point, which would be 40 centimeters from either side. Since this object is pivoting at 10 centimeters away, then we have shifted that pivot point 30 centimeters. And so that is what we call H, okay, the shift. Of course, we've done that many times before in our class. Let's go ahead and calculate what I should be for this object. So that would be 1/12 ml squared plus this shift mh squared. Well, we don't know what m is. You can kind of look ahead in the formula and see how the m's are eventually going to cancel out. It is not correct to cancel it out now, though. I have to leave that in as a variable and put my full length in there as if it were pivoting about the red dot, the center of mass. So that's the 0.8. And then, again, I don't know m, but I'm shifting by a distance of 0.3. Okay, and so that's how I would determine my inertia value. That comes out to be 0.143 times m. Okay, again, that m will eventually cancel out. By the way, I just noticed that I spelled oscillation wrong, and that really annoys me, so I'm going to bring it up. All right, so the inertia value is known, and we can then plug this into our formula. So period would be 2 pi times the square root of, here's our inertia, 1.143 times m, divided by m times g, we'll use 10, and h. So that h comes in again here. So it's going to be used in the parallel axis theorem, and then it's also going to be used in the actual formula for the period. We can, of course, see that our masses cancel out. The mass of this, the rate of swinging does not, the mass of the object does not determine the rate of swinging. And then we can go through and calculate our period. This comes out to be 1.37 seconds. So every 1.37 seconds, the rod would return back to its original position.